this bit by just doing a very quick recap of something I put on the board last week. And I'm going to rewrite it just to remind you about what a formula actually means. So we've got things like, for example, this is the recap bit. If you were to write the letter O, all right, now that just represents the element oxygen. It doesn't represent oxygen gas as such, but if you're going to be precise, that is one atom of oxygen, which doesn't really exist because oxygen doesn't have full shells of electrons, so oxygen usually goes around in pairs. So we're familiar with the formula O2. So that is one molecule of oxygen, and it's composed of two atoms joined together. All right, chemically joined together. Now, that's what the small numbers mean. They multiply up the number of atoms in a molecule, and we've looked at how to create a formula. But we then started looking at putting numbers in front. So if we were to put a number 2 in front of that, actually, no, it doesn't matter what I put in. If I do 2O like that, it's something that doesn't exist, but that is two atoms of oxygen. However, if we put 2O2, we've then got two molecules of oxygen and a total of how many atoms? Yeah. All right, so we've got 4 atoms altogether. Now, a formula is a fixed thing. So when you're balancing equations, you can't change a formula. But you can multiply the number of the formula that you've got. And the formula represents a whole entity, if you like, a unit of that substance. So, for example, H2O is one molecule of water. And you can multiply that up as much as you like. So we could have, 2,397 H2O. And that's 2,987, 300 even, yep, whoops. Let's try that again, till it's Friday. 2,397 molecules of water. But each one of those is H2O. So you can multiply up. I mean, that's a total of, I've now made it ridiculously difficult, but yeah, nearly 4,400 hydrogens and 2,397 oxygens altogether there. So then big numbers in front multiply the whole thing that comes after, everything that's in the formula, whereas the little numbers are only multiplying the preceding symbol, right? So in H2O, the little 2 is only multiplying the 2. Sorry, it's only multiplying the H. So it's 2 hydrogens and an oxygen, and water is always 2 hydrogens and an oxygen. So you can't change that. If you do change it, a change would make a different substance. So, for example, there is a substance which has the formula H2O2, but that's not water now. Water's H2O. That's a molecule of something called hydrogen peroxide you've probably heard of. Okay, but because we've changed the formula, we've changed the substance. But we could have, 5 H2O2, which would be 5 molecules of hydrogen peroxide. In other words, if you've got 5 molecules of hydrogen peroxide, you've got 10 hydrogen atoms and 10 oxygen atoms, because you've got 5 of everything in that formula. So when you're balancing equations, you have to have exactly the same on the left as the reactants as you have on the right, the products, because you can't suddenly just make something out of nothing, and you can't lose something. So the number of atoms that add up on the left and the number of atoms that add up on the right have got to be the same. So atoms in reactants must equal atoms in products, and that's why we do balancing. So atoms in reactants. No, not necessarily. Turn into atoms in products. All right, this is just a recap for those who missed it who are here, and for those who missed it who aren't here. All right, so they've got to be equal on both sides, so that's where you do the balancing. You put the big numbers in to multiply the number of molecules you've got. So that's recapping the principles of last session without actually using any particular equations. We'll come back to the equations in a bit. But what I want to do first this morning is to look at something slightly new that will lead us on to the idea of moles. Now, moles are important in terms of measuring concentrations, and that includes concentrations of things like medication, concentration of substances in the blood. So when you're looking at tests that are done on patients, or drips that might be set up, or blood glucose levels or something like that, knowing about concentrations in terms of moles can actually be useful. So we're going to look first at what is either known as, used to be known, I should say, as relative molecular mass, but because a lot of substances don't actually exist as molecules, that is not really a good expression. We more often, so I'm going to put it in brackets, more often call it formula mass, or we can call it molar mass, and that will make more sense as we go on to moles. And we have a symbol for this, and it's a uppercase M with a subscript R. I don't think it particularly matters whether that R is upper or lowercase, but what we're going to call this for now is formula mass. Now, you might remember, and I think this was way back in the physics, looking at the mass of atoms, atomic mass, yeah, because that's recorded on the periodic table, the atomic mass, yeah, and that was, so just to recap that bit, atomic mass is that, relative atomic mass, because we worked it out, didn't we, with the isotopes. So that was the average atomic mass, and it's on the periodic table. So if you look in any of the spaces on the periodic table, you get the symbol, you get the number, which is the number of protons, and then you get this, the average, the relative. Okay, that is the word I should have used, isn't it? Relative or average atomic mass, and that is on the periodic table. Now, hopefully, this is not a huge leap now, that if I say to you, what do you think formula mass is? Any ideas what the formula mass of something might be? All the atoms in it, their masses added together. Absolutely right. Yeah. So a formula mass, MR, is the sum of all the atomic masses in your formula. Right? So sum of those values in any given formula. So the problem that we have with this then is how many decimal places do we go to, because periodic tables always used to be done to nice round whole numbers, mostly. The one you've got, I think, does that go to 2 or 3? Is it the one on the wall? I can't remember how many that goes to. But 2 is fine. Okay, off your own periodic tables then. The relative atomic mass, let's take for hydrogen. What does it say on your periodic table for that? How many people have got? 1.008. Okay. What about the relative atomic mass for oxygen? 15.999. Okay. We know that those numbers come about because what we're doing is weighting it to meet the percentage of different isotopes that are in there with different masses. Okay. Now, this is the bit that's, it's not terribly difficult to take this step, I hope. The formula mass, or the relative atomic mass, then, for hydrogen as a gas, a molecule of hydrogen, if you like, what do we think the relative, the formula mass is for H2? It is 2 point, well, hang on, let me write it out. One of the things to do with chemistry calculations, it's always a good idea to write out your working. It's 2 lots of that. Okay, so it's 2.016. Simple as that. So the formula mass for oxygen would be, 2 lots of that. You can probably round it, I think. You could quite reasonably say that I would be very tempted to round that to 16 and say it's about 32. And so, the other thing that we just met further up, what about the formula mass for water? Well, how much of each?
Oh, so it'll be 2016.
Yep. Yep. Single oxygen. So that's 2 hydrogens plus a single oxygen. And that would be, okay, 18.015. We tend to say 18 because it's easier. So there's nothing particularly difficult about that. There is another angle on this, of course, is that some of these atoms are much bigger than others. I mean, the oxygen is way bigger than the hydrogen. It's about 16 times bigger. So in a water molecule, the oxygen actually has a much bigger role. And we know about water being polar and the influence that the oxygen has in there, don't we? So, that's a fairly obvious thing. But just in terms of the mass of a water molecule, which is obviously, not something we can actually weigh. But most of the mass comes from the oxygen. So, we could work that out as a percentage. What percentage is it actually responsible for? And what we're going to do next is to work through some examples where you're going to work out the formula masses, and then we'll see if you can work out the percentage masses as well, so that you can just see, how much each individual example contributes overall. Okay, if we have a look then at the first example you've got on this sheet, you're given the compound copper bromide, that is, a single copper atom with 2 bromine atoms joined to it to make bromide, so CuBr2, and then you've got a bit of space underneath that to do some calculating, but over on the side you've got a space to write the formula mass, and then it should say percentage copper, and it should say percentage bromine. The rest of them all have the percentage signs, but that one has lost its percentages somehow. So let's have a look then at calculating this. So the formula mass for this, what is the atomic mass for copper? Right, 63.549. Be very tempted to round that up, wouldn't we? And then the relative atomic mass for bromine on its own, just Br, would be? So
79.90.
Right. Okay, so to get the relative molecular mass, the MR, I'm sorry, I shouldn't call it that, formula mass, what we're going to need is I'm using up more space than you've actually got to do this, but you've got a 63.549 and then 2 bromines. So I'm just going to add them all up in a column. Which doesn't make life any easier, actually, to do it that way. But it just means I then don't have to put it into a calculator. If you've got a calculator, just check. But I make it 223.357. Yeah? So that's what goes in the top space. Okay, 223.357. I don't know what happened there. Now, the percentage of copper in that, well, there's 1 copper atom. There's only 63.549 out of that, which accounts for the copper. You haven't really got space to put the calculation in here, but I'm going to do that just to show that's how it works. 63.549, I should have stuck with the whole numbers, I think, over 223.357. That would be the fraction version, wouldn't it, of how much of that formula is copper. Of course, to get it to a percentage, you just do that and then multiply it by 100. So I'm now going to wait for an answer on that one. It's sort of a bit under a third. It's probably about a quarter, isn't it? Not quite. All right. So it's less than a... It is less than a third. Yes, of course it is. 28.45. Now, you could go through the calculation to work out the bromine, or you could just say, it's the rest, isn't it? Yeah? So that's an easy one because there's only 2 in it. So, yeah, 100% actually, minus the 28.45 will give us 71.55. All right, so those are the percentages. So the bromine actually makes up a much bigger percentage of that formula. All right, so it's just getting things in proportion a bit. All right, there are 4 more to do, but I'm not going to say do them all. I would say let's, just have a go at the next 2. The answers actually are on the back, so you can check those. The formula masses aren't there though. So I did steal this off a website. But so you have to work the formula masses out, but just do 2 and 3 just to make sure that you're getting the hang of this, and then we can move on to the idea of moles. Okay, so as long as you've got the hang of adding up the atomic masses to get the formula mass, then you'll be all right with what we need for the moles, because as I put at the top, molar mass is going to be the same thing. But what we're going to go on to now then is the section on moles, and I've given you a sheet which takes us through a sort of sequence really of logical ideas, I hope. So this sheet, the one that's headed up the mole, if we just have a look at what's on there, you can see that I've put little numbers next to the symbols, and that should take you back to the physical science bit where we were doing the isotopes, and that's representing the isotopes, all right, and it's representing their atomic mass. So where you've got the first one, it says 1 atom of hydrogen 1 has a mass of 1 atomic mass unit. Now that's that's a rounded version, all right. You've got it on yours as 1.008, but we're just using rounded numbers now. So if you take 1 atom of hydrogen 1, all right, hydrogen 1 has 1 proton and 1 electron. That's it. And all that mass comes from the proton. It hasn't got any neutrons. All right, hydrogen 1. So basically, 1 atom of hydrogen 1 has a mass of 1. 1 what? Well, you have to call it something, so they're called atomic mass units. That's what's on the periodic table. In comparison, 1 atom of carbon 12 has a mass of 12 atomic mass units. Okay. That seems reasonable. It's the same principle. Look at the periodic table. The atomic mass of carbon is 12. So one atom of carbon-12 has a mass of 12. And so the ratio of masses that you've got between those then is 1 to 12. All right, if you did hydrogen to carbon. Okay, now you've got some gaps coming in. 2 atoms of hydrogen 1 will have a mass of 2 atomic mass units. All right, so if we've got one of those, then you've got a mass of that. If we've got one of those, you've got 12. So now basically, if you multiply this up by any factor, the ratio is going to stay the same. So yes, if we've got 2 lots of hydrogen 1, that's a mass of 2 atomic mass units. So 2 atoms of carbon-12 will have a mass of 24. Yeah. All right, and again, the ratio is, it's 1 to 12, yeah, 2 to 24, down to the smallest, 1 to 12. It's got to be exactly the same. A carbon atom is 12 times bigger than a hydrogen atom. And equally, if we go on to 100 atoms of the hydrogen 1, we've got 100 AMU. And 100 atoms of carbon-12 would have a mass of 1,200. Yeah? If 100 atoms of hydrogen weighs 100, 100 atoms of carbon-12 is going to be 1,200 AMU. Yeah? And we still have a ratio of 1 to 12. Yeah. And getting into slightly larger numbers, not going to write it out. Oh, I might do. 1 million. Just to remind you how big some of these numbers can get. 1 million atoms of hydrogen 1 has a mass of, strangely enough, 1 million AMU. And then, as if it wasn't obvious enough, 1 million atoms of carbon-12 are going to have a mass of 12 million, yeah, 12 million AMU. So we're seeing a pattern here because we've still got a ratio of 1 to 12. Now there's a rather strange looking number down at the bottom there. 602, 000, 000, 000, 000, and so it goes on. And the way we would write that, and this really brings home to you why we need to use standard form, which was, you know, why we did it in that first unit. We keep it, we usually round it actually, we don't bother with that 2 in it, we usually just say 6 to be honest. But 6.02 times 10 to the power of 23. All right, so yeah, a lot of zeros there. 6 times 10 to the 23, that's a lot of atoms, of hydrogen 1, just happens to have a mass of, and you could say, oh, 6 times 10 to the 23 atomic mass units. Actually, yes. But for hydrogen 1, that happens to be 1 gram. Now, that's useful. Right? This number is ridiculous, but it's a very important one. So having given you that piece of information, if we then had, it should be 6.02, but I'm missing that out. But if we had 6 times 10 to the 23 carbon atoms, what do you think they'd weigh? 12 grams, yeah. Now, that number, that 6 times 10 to the 23, it's known as Avogadro's number. It was he was the guy who came up with it. But that is a mole. 6 times 10 to the 23, or 6.02 times 10 to the 23 is a mole of anything. So that is 6 times 10 to the 23 hydrogen atoms. That's a mole of hydrogen atoms. No, because carbon It's a mole is going to be its atomic mass or formula mass in grams. Yes, Jade?
When I took a toilet break, I'm a little bit confused.
Okay, we will go back to the beginning. Right. One atom. Yeah, you can't take toilet breaks, I'm afraid. But she's done this bit. It's all right. For those who are listening to this in recorded form, you can work out what's happening. One atom of hydrogen 1, that's the isotope, has a mass of 1 atomic mass unit. That's what you see on the periodic table. That's when you get the mass number on the periodic table, that's what's being recorded, if you like, the mass of 1 atom. The mass of 1 atom of carbon-12 is 12 atomic mass units. And then you multiply it up each time, but it keeps the same ratio. So if you had 2 atoms of hydrogen, 2 atomic mass units, 2 atoms of carbon-12, 24, because you're doubling what you started with, yeah? Keep going, 100 hydrogens, 100 units, 100 carbons, 1200. 1 million hydrogens, 1 million units, 1 million carbons. 12 million units. And then this bit, this is just something that you're not supposed to know, right? You will after today, that this particular number, 6.02 times 10 to the power of 23, just so happens. All right. Now, how Avogadro ever worked that number out, I have no idea whatsoever. I can't even start to imagine how you work that out. I'm sure, but it is, and it's over the other side. It tells you it's Avogadro's number. And that number is known as a mole. All right. So let's put it in properly, 6.02. 6.02 times 10 to the 23 of anything is a mole. So you can have a mole of hydrogen atoms. They weigh 1 gram. A mole of carbon atoms weigh 12 grams because it's the same number of each of them, but carbons are 12 times bigger. So they weigh 12 times as much, and it just happens that that's the molar mass. So what would be the molar mass for a mole of hydrogen molecules, H2? 2 grams, yes.
Molar, is it M-O-L-E-R?
No, A-R like the teeth, molar. So molar mass, or formula mass, it represents that many particles, if you put it in grams, all right? So 6.02 times 10 to the 23, stupid number, but I'm going to make it even stupider in a minute because we have a song for it. But I will not be recording that. Anybody who's listening to this, who wants to listen to the song, there should be a link on Moodle. 6.02 times 10 to the 23 then is 1 mole. So we can have a mole of hydrogen, we can have a mole of carbon, a mole of water, a mole of sodium chloride. You could, if you wanted, have a mole of moles. All right, I should add to the people listening to this that I am holding up a furry stuffed mole. Otherwise that doesn't really make any sense, does it? So a mole is just a number of particles. Now, you're never going to have to work with that number, 6 times 10 to the 23, because we just happen to know then that that's, if you're talking 1 atom reacting with 1 atom to give 1 molecule, then we know that it's actually going to be 1 mole reacts with 1 mole to give 1 mole.
So I'm 150 pounds. If I was to do 6.02 times 10
to the 23
times,
yeah, but you can't. You can't. But you're not. Well, no, because you're not one substance. We would need to know the molar mass of something to work out what a mole of it weighs. Yeah, and I'm going to show you some examples. I've got a trolley with some examples of moles on them. Oh, I'm going to give. There's a calculation on here that we're going to try in a bit, which we'll listen to the song first, just because it's so silly. But if we were to take a simple equation like, let's do the sodium hydroxide plus hydrochloric acid. It would make sense to put the H first, wouldn't it? HCl gives you sodium chloride and water. All right, we've done that quite a few times, that one. What it looks like that's saying, and what you've been balancing up, is the fact, well, you've got one sodium on the left, you've got one sodium on the right, you've got one oxygen on each side, but we've got a bit of a problem. No, sorry, our hydrogens do balance in this one, don't we? We've got one in the sodium hydroxide, one in the hydrochloric acid. That balances with the two on the other side, and the oxygen balances. So that whole thing balances, yeah? And what it appears to be saying is that one molecule of sodium hydroxide will react with one molecule of hydrochloric acid to give us one molecule, even though they don't exist, of sodium chloride, and one molecule of water. But of course you could scale that up. You could double it all the way through and it still says the same thing. You could have 2 plus 2 gives 2 plus 2. But of course what it's also saying is 1 mole reacts with 1 mole to give 1 mole and 1 mole. Yeah? So although this is a ratio here of, say, 1 plus 1 gives us 1 plus 1, and that might be atoms, it could be moles, because 6 times 10 to the 23rd will react with 6 times 10 to the 23rd to give you 6 times 10 to, yeah, and so on. Yeah?
Can I ask, when you're doing things like this, do they always have to be equal?
In what sense? When equal?
Well, if we're doing it all and it has that side has to add up to
you've-
the same as that side.
you've
Can
got-
you do it when it's that?
You've got to have exactly the same number of atoms in your reactants as you have in your products, because you can't suddenly get some from nowhere and you can't suddenly lose them. You've got to retain them. And that was pretty much the first law of thermodynamics that we looked at early on, that you can't create or destroy energy or matter. You know, you can just convert it from one form to another.
So then that makes this always easier to work out.
It should, yes. So if we had, you'd got another one where it had to be balanced. So we had this one, going back to last week's examples. If we react magnesium with hydrochloric acid, you get that. Sorry, you don't get water at the end, you get hydrogen. I was just wondering where that oxygen had come from. That's what you can't do, so you can't just make something that's only on one side. Now what this one is telling us, that yes, one atom of magnesium would need 2 molecules of hydrochloric acid, and that would produce 1 molecule of magnesium chloride and a molecule of hydrogen. But of course you could multiply that up by any amount. So what we are actually saying is 1 mole of this plus 2 moles of that would give us 1 mole of that and 1 mole of that. Right, okay. If I give you 12 grams, no, not 12 grams at all, 24 grams. If I was to give you 24 grams of magnesium, what mass of hydrochloric acid would you need? No, because a mole of hydrochloric acid is going to have the mass of hydrogen plus the mass of chlorine added together. All right, HCl, I've jumped way ahead here, but it just seemed to fit. HCl has the formula mass of 1 and 35.5 roughly, so 36.5. So in order to react with 24 grams of magnesium, you would actually need no, that would be 1 mole. Up here, HCl has the formula mass of 36.5, doesn't it? So 1 mole of HCl has a mass of 30. Yes, yeah, in grams. Yes, so 73 grams. So you'd need 73 grams. All right. Now later on this morning, hopefully, you're going to predict how much of something you can make, and then you're going to do the reaction, and next week you're going to weigh it and see if you made that much. And it's making copper sulfate, the blue crystals. I can't remember whether we've come across those. I might have some. No, I think I have. But you could also work out what we get on the other side. Now, the masses won't necessarily match. Well, let's see. Actually, they should do, shouldn't they? Because we're adding up exactly the same atoms. I'm talking rubbish there. The molar mass or formula mass for magnesium chloride would be, we got, yeah, for that, yeah, it's a 24 plus the 35.5 plus another 35.5. So those two added together make 71. Is it 95? 95 grams of that. And then a mole of H2 has a molar mass of, well, what's its formula mass?
2 grams.
Yeah, so it's 2. Okay, so do they add up? I rather think they've got to. So yeah, 97 on both sides. So we haven't gained anything, we haven't lost anything, but they've moved about. Now, hopefully you can see why that starts to become more useful, because it means that we can actually work in masses. You can weigh something out and react it with a known quantity of something else, and you know what you're going to get. Yeah?
Oh, yes. So I was confused with the 36.5, but I realised you
Yeah,
double it.
that's right. The 36.5 up here is a single H and a single Cl. So that's, yeah, that's 2 lots of 36.5. All right, now that has jumped ahead, but I think, you know, there will be use to that, and we'll come back to that. So we're going to talk a little bit more about moles. And I'm going to show you the mole song. It's a ridiculous, silly song, and it's way out of date as well, because it talks about the number of people on the surface of the Earth, and it's been updated, I think, from 5 billion to 6 billion, but actually there's now 7 billion. So it talks about that in terms of how many moles of people, I think, that sort of thing. But it's people actually doing things like eating a mole of marshmallows and that sort of thing. But it makes the number 6 times 10 to the 23rd stick in your head. And it is a very silly song. Like I say, it should be on a link to it on Moodle for those who are listening to this. Okay, if we go back to the sheet then, and we go over the other side, you can see a bit of background information on what a mole is then. Unit of measurement in chemistry, it expresses amounts of chemical substance. And the definition is, it's an amount of a substance that contains as many elementary entities. Now, that could be atoms, it could be molecules, it could be ions, it could be electrons. As there are atoms in 12 grams of pure carbon-12, and you'll be thinking to yourself, well, why are we comparing it to carbon? Why not hydrogen? Well, it's because there are, you've always got to have a reference point. There's no reason why you should use hydrogen, and carbon-12 is chosen as the, you know, the reference isotope. Carbon-12 is what we always compare against. And it then gives you that information about it being Avogadro's number. And the unit that we use for mole is just MOL. All right, we don't have to write the whole thing out, but that's the unit that we use. All right, so we've seen the song and heard the song, and now we have a question. If an average person consists of 30 trillion human cells, how many people would equate to a mole of human cells? If you're just rough estimate in your head, you know, what are we talking? Hundreds, thousands, millions, or what? What? Okay. Person.
How does 30 trillion relate to 6.7?
All right. Person is 30 trillion. That's 30,000, 30 million, 30 billion, 30 trillion. Yeah? That's how many cells there are in a person. Yeah?
There's only 13.
Right. Well, 1 mole of cells, I haven't got room to write it all in, is 6. Let's leave out the 0.02 because it makes it easier with the 6 and the 3 there. Is that many cells?
6 and 23.
Yeah. So, how many people would you need to get a mole of human cells? How would you work it out?
Is it 1 point something?
No. 6 and 3 are the magic numbers here.
Well, there's 12 rows, isn't there? 12 zeros?
13.
13 zeros.
13 zeros
And
there.
we need to get 23 zeros.
We do.
Will it be less than the 2 people?
No. Because if you multiplied, well, what would happen to the person number up there if we had 10 people? It only had an extra 0. Each time you multiply by 10, it adds an extra 0. So if you had 100 people, you'd add 2 extra zeros. 1,000 people would be 3 extra. No, because you multiply, it's 10 to the power 13 to get the numbers up. It's not as simple as that. No. 6 times 10 to the 23 is our mole. So how many people can we get into a mole then? Yeah? Right, let's express our person in standard form like that. How do we write 30?
Times 10 to the power 30.
That's it. Well done. Now, something we haven't done, and something you may not have done in GCSE maths, I suspect, is how you work with powers like that.
I just do it every day.
If you divide, well, we can do this a bit at a time. We can do some cancelling out. Could we cancel out the 6 and the 3 for a start? Yes, you can, because if you divide the top and the bottom by 3, you lose that, and that turns into 2. You've divided the top and the bottom both by 3. We've done the same to the top and the bottom, yeah? So it stays the same. It's 1. Yeah, so we've lost that, really. Okay, if we divided the top by 10, that would come down to 10 to the 22, wouldn't it? And if we divide it by 10 again, it'd be down to 10 to the 21. If we divide it by 10 again, it'd come down to 10 to the 20. Each time you divide that by 10, you lose 1, don't you? Well, because if you think, that times that times that times that is 10 to the 4. If we divide by 10, we lose one of those. Yeah? So if we divide the top, let's divide the top and the bottom by 10 to the 13. We are absolutely right. We are left with 10 to the power 10. 2 lots. So the actual answer, the number of people...
Is that the same?
Nope. The number of people is 2 times 10 to the power 10. Right, now to write that out, that's 2 times 10, yes, so times 10, and then 2, 3, 1, 2, 3, 1, 2, 3 people. You need that many people to get a mole of human cells. It's 20 billion. How many are there on the Earth? About 7 billion. So it's about 3 Earths of people. Yeah, you can copy that out if it helps. All right, but it's just the size of this number is ridiculous, isn't it? Okay, all right. So if a person is, that's the bit of information you've got on your sheet, right? A person is 30 trillion cells. All right, this would have been, we could write that there as 10 to the 3 times 10 to the 13. All right, but a mole is clearly a lot more than a single person, and it doesn't look like it's that much more until you realise that you're multiplying by 10 and then by 10 again and then by 10 again. And it's not just adding tens, it's multiplying by 10. And then when you multiply 10 by 10, it's times 100, and then by 10 again, it's times 1,000. It just increases more and more. All right, that's not something that you need to know, but it's just to get your head around the the actual numbers there. Now, I think I've probably given you sheets that have got an error on in the next little bit. I'm not sure. We will see. There's a little table underneath. If you're not writing that down, because you don't need to, then you could look at the next bit. What it should say in the table that you've got, it should say 1 mole of magnesium 24. Does yours say 12? Right. Get rid of that and give you one that says, you haven't written anything on there, have you? Otherwise, have one with a 24 on it. That should say 24, not 12. You can just cross it out if you're happy to do that, yeah. It's been an error that's pursued me for years, and I have corrected the sheet, but left the old ones in the drawer. So, get rid of the 12s. Apologies for the... No, probably not. Apologies for the silent gap there in the recording, because I just went to the bin. Moles are important. I mean, for example, if you've got somebody with diabetes, it is still measured in millimoles per litre. So, you know, the uses of it, it is a standard unit for the amount of stuff, so it is a useful one.
Oh, also, can I ask you about the presentation? Basically, apply for
Yes.
Can I do that?
Yes. Yeah. Right. Now, what we should have on that little table on the sheet, then, 1 mole of magnesium 24 will have a mass of 24 grams. 1 magnesium of oxygen 16, but O2 would be now 32 because it's O2.
Oh, yes.
Yeah. 2 moles of water. Yeah. Well, oxygen's 16, hydrogen's 1. So 1 mole of water would be 18. So 2 moles of water, 36 grams. Half a mole of sodium chloride. Well, sodium's 23, chlorine's 35.5.
33.5, you think?
35.5. 23 plus 35.5.
58.5.
So half of that,
Add them together, then half.
you add them together, then you half it.
20.
29.25 sounds about right. And then 0.1 of a mole of that stuff, which is sulfuric acid. Yep, 2 hydrogens, 1 sulfur, 4 oxygens. I'm going to do it to round numbers. I hope I've got that right. 98. So 0.1 mole. It is. Yep. You divide through by 10, so it's 9.8 grams. Yeah.
So where's the next one? 1 nitrogen, 8 hydrogen, 1 carbon, and 3 oxygen.
Yep. Okay, the next one then. I would choose awkward ones, wouldn't I? Yeah, we have 2 nitrogens, so that's 28. 8 hydrogens, we'll call that 8. The carbon, which is 12, and 3 oxygens is 48. whatever that is. 20, 48, 48, 96. And so this time we've got 0.01 moles. We divide through by 100, so it is 0.96. Right, I think we're getting the hang of this, which is good. All right, now the other bit that's on that sheet actually takes you through what I'd already done on the board, which is the fact that if you've got a chemical equation, although we've been thinking of it in terms of, one atom, one molecule, scale that up, and of course 1 mole, 2 moles react together. And because we know what they weigh in grams, of course then we can weigh how much of something we get from how much of something we put in, and there's a lot of calculations that are very usefully done through that. I think we'll take a break at this point. I mean, it's we've gone a bit further perhaps than we would normally before break, but I think we'll stop at that point, and then when we come back, we will do the calculation to try and predict what we'll get out of the practical. Then we'll do the practical. Now that leaves some more examples and things to do, but if we leave those till the beginning of next time for a sort of recap before we look at the assignment, then that hopefully will be a bit of a help to people who aren't here today as well.